Welcome to today's class. So today we discuss about the important topic of dynamic programming. So in this topic, we can learn about the different models of dynamic programming models. What is the difference between dynamic programming problem and linear programming problem? Different notation and definitions, and the characteristics of dynamic programming problem and the algorithm of dynamic programming problem. So, what is actually dynamic programming? Dynamic programming is a mathematical technique dealing with the optimization of multi-stage decision process. The more significant name of dynamic programming is recursive optimization. The mathematical technique of optimizing a sequence of interrelated decisions over a period of time is called dynamic program. So, again, I'm explain here, dynamic programming is a mathematical technique. We use this technique to solve the linear programming problem. The word programming has been used in the mathematics in the sense of selecting an optimum allocation of resources, and it is dynamic as it is particularly useful for problem where decisions are taken at several stages, such as every day and every week. Richard Bellman developed this technique in early 1950 and invented its name as dynamic programming. Nowadays, this dynamic programming is also very useful in computer subjects. The more significant name of dynamic programming is recursive optimization. Actually, in dynamic programming, a large problem is divided into small sub-problems or sub-programs, each of them involving only a few variables. This technique converts and split into number of subprograms. Let us consider the technique used to convert one problem of n variables into n subprograms. Each program consists one variable. The optimum solution is obtained in an orderly manner, starting from one stage to next stage, to the next stage, and so on. Recursion equations are standard nature, and its computer program runs in a standard routine. So what happened actually? The decision making process in several decisions to be taken at different times. For example, of dynamic programming, problems of inventory control, evaluation of investment opportunities, long-term corporate planning, and so on require sequential decision making. One good example is how to minimize the inventory cost of a company for a year. If this is actually problem here, now we can split the problem into different sub-problems or sub-program. Monthly, if you calculate monthly the inventory cost and try to minimize month-wise, at the end of the year, automatically we get the optimal solution. So in general, the mathematical technique of optimizing a sequence of interrelated decisions over a period of time is called dynamic programming. The dynamic programming approach uses the idea of recursion to solve a complex problem broken into a series of interrelated sequential decision stages, also called as sub-problems or sub-programs, where outcomes of a decision at one stage affects the decision at each of the following stages. Just I am explain the example how to minimize the inventory cost of a company year-wise. Now we discuss about what is the difference between dynamic programming problem and linear programming problem. As we know, in linear programming problem, there is a systematic algorithm. On the basis of that algorithm, we can solve the problem. In dynamic programming, there is no set procedures or algorithm as in LPP to solve any decision problem. The dynamic programming technique allows breaking the given problem into a sequence of easier and smaller sub-problems. What is the meaning of this? The entire problem is divided or breaking into smaller, easier sub-problems, which are then solved in a sequential order. The second point is linear programming approach provides one-time period, that is single-stage solution to a problem, whereas dynamic programming problem approach is useful for decision making over time and solves each sub-problems optimally. So this is actually two basic difference between the dynamic programming and linear programming problem. Some terminology we are used in dynamic programming problems. That is, one is your stage. This is an important word, stage. Another important word, that is state. Another important word, that is known as a return function. What is actually a stage? The dynamic programming problem can be decomposed, means split or divided into a sequence of smaller subprograms called stage. At each stage, there are a number of decision alternatives or course of action, and a decision is made by selecting the most suitable alternatives. Stages very often represent different time period in planning period of the problem, place or other entities. For example, in the replacement problem, each year is a stage. In the salesman allocation problem, each area represents a stage. So what is the meaning of this? Stage means the entire program or entire problem is split into different subprograms, and that subprograms is called as your stage. Then the important word is state. The variable that links up two stages is called state variable. Each stage in a dynamic programming problem has a certain number of states associated with it. These states represent various conditions of the decision process at a stage. The variable that specify the condition of the decision process or describe the status of the system at a particular stage are called state variable. In general, the variable that links up two stages is called state variable. Suppose there are 5 stages and the link between stage 1 and stage 2 is called as a state. Similarly, stage 2 linked with stage 3, that is called as another state. These variables provide information for analyzing the possible effects that the current decision could have upon future course of action. At any stage of the decision-making process, that could be a finite or infinite number of states. For example, a specific city is referred to as state variable in any stage of the shortest path problem. So this is not a state. Then another word that is known as return function. What is actually return function? The return function is generally depends upon the state variable as well as the decision made at particular state. That is actually the definition of the return function. In general, I am explaining here at each stage a decision that can affect the state of the system at the next stage and help in arriving at the optimal solution at the current stage is made. So in the beginning, I already told that all the stages are executed sequentially till we get the optimal solution. Every decision that is made has its own merit in terms of worth or benefit associated with it and can be described in an algebraic equation form. This equation is generally called a return function since for every set of decisions a return on each decision is obtained. This return function is generally depends upon the state variable as well as the decision made at a particular stage. An optimal policy or decision at a stage executed optimal, that is maximum or minimum return for a given value of the state variable. So what happened? A small example, if you consider shortest path between two cities. Suppose there are two cities, one is A, another is B, and a salesman travel from city 1 to city 2 or city A to city B. But other places are there. So the job of the salesman is to cover the shortest path to reach from city A to city B or city 1 to city B. At that time, we have to find the optimal solution, that means the minimum shortest distance. If it is mentioned in the time, we calculate the minimum time to reach from source to destination. So these are the programming terminology basically we use in dynamic programming. Then we discuss about decision tree and Bellman's principles. So decision tree, what is actually a decision tree? A decision tree is a multi-stage decision system in which each decisions and state variable can take only finite number of values, can be represented by a decision tree. Circles represented nodes corresponding to the stages and lines between circles denote the arc or line corresponding to decisions. The dynamic programming techniques deals with such situations by dividing the given problem into subproblem or stages. Bellman's principles of optimality. First, what is actually a decision tree? As we know, decision tree means there are number of nodes and it is represented by using a circle, and each nodes are joined by arc or by a straight line, and we can arrange the nodes in the stage wise, stage 1, stage 2, stage 3 in this way because it's the tree like structure. As we know in the computer, Decision tree means there is a special node. It is called as your parent or the beginning or the starting. That is the state. We indicate it is at stage 1. Then in this way, we go for the second level, that is called your level 2 or stage 2. In this way, all the decisions or all the stages are interlinked by different state. So the dynamic programming techniques deals with such situation by dividing the given problem into sub-problem or stages. So Bellman's principles of optimality means it states that an optimal policy, Bellman's developed a policy that is called an optimal policy has the property that whatever the initial state and decisions are the remaining decisions must constitute an optimal policy with regards to the state resulting from the first decision. It can be represented mathematically. What I am writing in the slide, look the slide, that is function of x equal to max, that is r of dn plus function of s minus 1 and t of x and dn. There are two variables where f of x is called as the optimal return from n stage process when initial state is x. We start from the initial state. And r of dn equal to immediate return due to decision dn. Then t of x comma dn is represented as the transfer function which gives the resulting state x equal to set of admissible decision. Set of admissible decision. Then we discuss about the characteristics of dynamic problem. The basic features or characteristics of dynamic problem is the problem can be subdivided into stages. That is the first characteristics. The problem can be subdivided into stages. A complex problem is divided into stages. A stage is divided into sequence the decisions. That is dynamic programming problem. Decomposes a problem into sub-problems such that the optimum solution of the problem can be obtained from the optimal solution to the sub-problems. Every stage of dynamic programming problem consists of a number of stages associated with it. That is the second step or second characteristics. Then the third characteristics is decisions at each stage consist the current state into state associated with the next stage. The state of the system at any stage is described by a set of variables called state variables. Means a dynamic programming problem associated with these two terms. One is your stage, another is your state. When the current state is known as optimal policy for the remaining stage is independent of the policy of the previous one. Then, to find the optimal policy for each state of the system, a recursive equation is formulated with n stages remaining given that optimal policy for each state with n-1 stages left. Using recursive equation approach, each time the solution procedure moves backward stage by stage for obtaining the optimum policy of each state for the particular stage till it attains the optimum policy beginning at the initial stage. Then we consider forward computational procedure or backward computational procedure. After dividing the whole problem into different sub-problems or different stages, then we find out the states, then we go for calculation the optimal solution by using forward computational procedure or backward computational procedure. The dynamic programming problem is solved by using the recursive equation starting from the first through the last stage, that is obtaining sequence F1, F2 up to Fn. The computational involved is called forward computational procedure. That means if you start from the first stage to last stage to find the optimal solution, that is called as a forward computational procedure. Similarly, if the recursive equation is formulated in such a way that the sequence is from the backward, that is, or that means Fn, Fn minus 1, then up to F1, then the computational is known as backward computational procedure. So we can solve the dynamic programming problems by using two ways: forward computational procedure or backward computational procedures. Then we discuss about the algorithm of dynamic problem. It's very important. There are 5 steps or 5 procedures. What is the first one? The step 1 indicates identify the decision variable and specify objective function to be optimized under certain limitation if exist. So you have to find the decision variable first and specify the objective function, just like in our LPP, linear programming problem, to be optimized under certain limitation if exist. Then second step is divide the given problem into sub-problems. Divide the given problem into sub-problems. That is the main important characteristics of dynamic programming. Remember, identify the state variables at each stage. State variable means the status of each stage, and write down the transformation function as a function of the state variables and the decision variables at the next stage. Suppose if you consider a decision tree, the first node is, I mentioned there, discount policy of a shop. So discount policy means number of customers visit to that shop every day, and the owner plan to give a discount to the different customers to maximize the profit. To maximize the sales in this way, it automatically the profit will be increased. So decision policy means there are different types of customers. Sometimes a dealer may visit, sometimes a retailer may visit, sometimes the customers visit to that shop day-to-day basis. Then you plan that here we plan to give the discount policy to different customers. The customer may be a single individual, or the customer may be a retailer, or the customer may be a dealer. What happened actually? At that time, the shop owner give the discount to different types of customers. And you can represent that thought, that policy by using a decision tree. By using a decision tree. And these are the known as the stages. Suppose an individual customer comes to purchase an item more than 2,000 rupees, you give a discount of 10% on the total amount if the customer is an individual. If the customer is a retailer, you give a 20% discount to the retailer. If the customer is a dealer, you give 30% to the dealer. So these are the actions to be executed. That is called as your decision variable. Then write general recursive relationship for computing the optimal policy. Decide whether forward or backward method is to follow to solve the problem. As I am explaining the characteristics of dynamic programming problem, forward or backward computational process. Then step 4, construct appropriate stages to show required values of the return function at each stage. Then step 5, determine the overall optimal policy or decision and its value at each stage. There may be more than one such optimal policy. Now this is a meaning of how to determine the overall optimal policy or decision and its value at each stage to get the optimal solution. So these are the steps in dynamic programming problem. Then solution of problem. Then solution of problem. The solution of problem by dynamic programming is usually done in two stages. Number 1, the development of functional equation for the problem. Number 2, to solve the functional equations for determining the optimal policy. Now I am explaining here. Unlike linear programming, there does not exist a standard mathematical formulation, as I am told earlier, of the dynamic programming problem. This is a general type of approach to problem solving, and functional equations used must be developed to fit the individual situations. Similarly, dynamic programming theory, however, developed the so-called functional equation approach, which offer a unifying but not fixed format of expressing the decision problem mathematically. So these are the solution, two types of dynamic programming solution problems process we follow how to solve the dynamic programming problem. Then again I am explain what is the importance of this dynamic programming problem. Many problem involves taking decision over several stages in a sequence. Consider, for example, a production planning situation where a company has to decide on the production plan of an item for the next 3 months so as to meet the demand in different months at minimum cost. Assume that it does not have any stock to start with. The different months for which the production is to be decided constitute the stages. Taking the best decision month by month may not be optimal policy in such cases. The relevant costs are the fixed cost of the production in any period, which is involved only if production is undertaken in that period, and the inventory carrying cost per unit per period on any inventory left at the end of a period. Then, if the fixed production cost is very compared to the inventory carrying cost, it is always better to produce all demands in the first period itself. A period by period decision in such cases can never suggest carrying inventory to be optimal, and hence can never lead to the optimal plan. Linear programming formulation of such problem are possible, provided the objective function and the constants can be expressed as linear functions. In the given situation, the objective function is not linear. Hence, dynamic programming problem provides us with an alternative methodology for solving such multi-stage problems involving decision over several stages in a sequence. By the very nature of any planning problem, decisions are called for in every period so that the multi-stage aspect is essentially inherent in such problems. Associated with each stage or period are input data, decision variables, output parameters, and objective functions. The stages can be thought of to be connected in series, in a sequentially, with the output of a stage forming one of the input to the immediately succeeding stage. After one stage, you move to the second stage. Finally, for determining the effectiveness of the decision taken, the objective functions of the problem is arrived at from the individual objective functions of the stages. In the example above, for each month, the input data are the beginning inventory and the demand. The decision variable is the production quantity. The output is the end inventory. And the objective function is the cost expressed in terms of decision variable. The stages are essentially linked in series. At the end inventory of any period is the beginning inventory of the immediately succeeding period. Means after completing one stage, whatever output you get, that will be the input for the next stage. Once such characteristics is achieved for a problem situation, it is possible to apply dynamic problem formulation and solution. So this is knowledge of the dynamic programming problem. Then I go through one example how to solve a numerical problem by dynamic programming problem principles. Let us consider a medicine manufacturing company. A medicine manufacturing company has 5 medical representatives working in 3 sales areas. Means there are 3 areas. Area 1, Area 2, Area 3, or you may consider as Area A, Area B, Area C. But in my question, I mentioned it as Area 1, Area 2, and Area 3. The profitability for each representative in 3 states area is given in the tabular format. So what happened actually? In the question it is mentioned number of representatives and 3 areas are there, area 1, area 2, area 3, and the profitability is mentioned in the column wise. Suppose, for example, one representative working in area 1 and the profitability is 47,000 because all the values that is mentioned in the table, in the question, in the table, it is in thousands, in rupees. So 47,000. Suppose one representative is working in area 2, the profit is 47,000. If one representative is working in area 3, the profit is 56,000. Similarly, suppose 3 representatives working in area 1. What is the profit? It is mentioned in the table, that is 72,000. If 3 representative is working in area 2, the profit is 66,000. If 3 representative is working in area 3, the profit is 72,000. So how many representatives are there? 5 representatives. That is mentioned in the question. A medicine manufacturing company has 5 MR. MR means medical representative who work in 3 sales area in different area. And the profitability in thousands are mentioned. If suppose no representative working in different area, what are the profitability? That is 32,000 in area 1, 37,000 in area 2, and 44,000 in area 3. If total 5 representative in working simultaneously in area 1, the profitable is 92,000. Similarly for area 2, that is 84,000. Similarly for area 3, that is 97,000. So that is mentioned in the question, and the question asks you, find the optimal allocation of representative to maximize the profit. Means that is our job. You allocate the number of representative in different area. You may consider the 2 representative in area 1, 1 representative in area 2, and 2 representative in area 3. In total, that is 5 representative. In total, that is 5 representative working in 3 different areas. So we have to find the best solution, optimal allocation of representative to maximize the profit. So this is our question. If you go through this question, then what is the solution? We have to find the stages and the state variables, and then we can solve the problem. The solution is like that. There are 3 areas which are represented as 3 stages, and number of representative is known as state variable, and number of representative is known as state variable. So that is a bigger job. First I consider the stage 1. I am considered stage 1. In stage 1, I think I start from area 1. I am taking a single area. That is area 1. That is a stage 1. So in stage 1, what happened? As per the question, number of representative is given, area 1 is given. So I mentioned here, number of representative 0, 1, 2, 3, 4, and 5. What are the profit? That is 32, 47, 62, 72, 81, 92. I am consider the first area. The first area is my first stage, and I have mentioned the number of representative working in that particular area and what are the profits. I mentioned in the table. After the stage 1, we move to the stage 2. What happened in stage 2? In stage 2, we consider 2 areas, area 1, area 2. We may also consider area 1 with area 3, but here I am considering the area 1 and area 2. Now consider the first 2 area, area 1 and area 2. But what is the limitation here? 5 representatives can be divided among 2 areas in 6 different ways. In 6 different ways means from 0 to 5. That is 6 different ways. So here we consider the 2 area profitability, and we have to find the maximum profitability. So for stage 2, this is the table. In the first row, I mentioned it is area 1. I am taking that is the variable x1. I am writing here 0, 1, 2, 3, 4, 5. This is the x1 means the number of representatives. And in the second row, I am mentioning here the function of x1, that is the profit. As per our question, I am mentioning here 32, 47, 62, 72, 81, and 92. Now I am considering in the stage 2, that is, I am just take the area 1 and area 2 and add this profit, both the profits as per the constraint. That means 5 representatives working in 2 different areas and find the maximum. So I am taking as x2 and f2 x2. x2 is the number of representatives for area 2 and function of x2 indicates the profit in thousands as per the question in area 2. Then what I am writing here? In the third column, I am writing here 0. What is the profit? 0 means what? No representative. What is the profit? 32. And in the fifth row, I am mentioning that is 0 in the matrix format. That is 0, the profit is 37. If 0, 0, no representative, then what is the profit? I am add this one, 37 plus 32, that is 69. Similarly, 0 representative in area 2 and 1 representative working in area 1, then what is the profit? 47 plus 37, that is 84. If 2 representative is working in area 1 and 0 representative is working in area 2, if I am adding this, that is known as a 62 plus 37, that is 99. In this way, if you proceed, that is 3 representative in area 1 and 0 representative in area 2, that is 109, and 4 representative in area 1 and 0 representative in area 2, it is 118, and 5 representative is working in a particular area 1, and 0 representatives means nil representative is working in area 2, then if I am adding the profits 92 plus 37, that is known as 129. Now come to the next row. In area 2, 1 representative working, we get the profit that is 47,000. And in area 1, 1 representative will be working, that is the profit is 47. If I add this 2, what is actually result? That is known as 94,000. In this way, I am creating a table. In this way, I am creating a table. But what is keep in your mind? Total 5 representative working in different area. So in the 6th row, look, in the 6th row, what I am writing here? 1 representative is working in area 2 and in the 7th column, 4 representative is working in area 1. If you combine, what is happen? 4 plus 1. That is 5. That is the limitation, that is the constant mentioned in the question. Then what is the profit here? 47 plus 81. That is now 128. In this way, we calculate all the values for area 1 and area 2. After that, we calculate the maximum profit. After adding the profit of area 1 and area 2, we calculate the maximum profit diagonally from this table. So 0, 0, we get 69. That is actually highest profit. That's why I'm marking it as in the bold, 69. Then diagonally, if we move 79 and 84, 1, 1, 79 and 84, 84 is maximum. So I'm marking as bold, that is 84. Then 86, 94 and 99. 99 is the highest, is the maximum. So that's why I mentioned it as in the bold letter, 99,000. And 109, 98, 101, 109, 109. Here 2 109 is there, that's why I'm bold it. These are the maximum profit. And at the end, 129 is the maximum profit. If you consider, if you draw this table, it's very easy. Take the area 1, take the area 2, add the profit of the area 1 and area 2 as per the repetitive mentioned in the question, and you get, you just collect what are the highest or the maximum profit. After calculating, we go to the stage 3. 5 representative to be allocated to the 3 areas. That's I am mentioned here. Number of representative, that is 0, 1, 2, 3, 4, 5 in the first row. And the total profit what we calculated in this table is mentioned in this revised table. Total profit, that is function of x1 plus function of x2. That is rather 69, 84, 99, 109, 119, 129. Then third row I am representing here a representative in area 2 and area 1. So what happened in this row I am mentioning here, look here, 69 by the combination of 0, 0 representative. 84 is the combination of 1 and 1. That's I am mentioning here. 0 plus 0, 0 plus 1, that is the 84, 0 plus 2, that is 99. Here, then 99 and 109. 99 and 109. So here I am mentioning here 99 as 0 plus 2 and 109. 2, 109 is there. So 0 plus 3, 0 plus 3, 0 plus 3, and again 1 plus 3. I am mentioning in the here under 109. So 0 representative actually in area 2 and 3 representative working in area 1. That is 3 representative total. What is the profitable? 109. Similarly, 1 representative is working in area 2 and 2 representative is working in area 1. Then the maximum profit is 109. Similarly, 119 is generated by using the 1 plus 3 and 129 0 plus 5. So these are the data whatever we collect in the previous table I mentioned here. Then we take the third area, that is area 3. So number of representative of area 3, I am mentioning here the backward, because in the first column heading you write 0, no? In the number of representative area 3 I am mentioning is a 5, because if you add, that is 5, total 5 representatives. Similarly, whenever you mention as 1, below you mention as 4. Whenever you mention as 2, on the top, below you mention as 3. Because 3 plus 2, that is 5 representative, that is total 5 representatives working in 3 different areas. That's I am writing here. Again 3, then 2, again 4, then 1, again 5, then 0. That's why number of representative area 3, 5, 4, 3, 2, 1, 0. Then what are the profit? As from the question, we know that when for representative 0, the profit is 44. For representative 1, the profit is 56. For representative 2, the profit is 62. For representative 3, the profit is 72. For representative is 4, the profit is 84. For profit is 97 when number of representative is 5. Then by taking this data I am putting here. Number of representative area 3, 5, 4, 3, 2, 1, 0, and I am putting the data here. That is 97, 84, 72, 62, 56, 44. Then we add total. What is the total profit? From the first table, from the previous table or first table, we calculate by taking 2 area and we collect the maximum profit. Then here we add this 2 2 areas profit in the third areas. That is, I am getting 166, 168, 171, 171, 175, 173. After finding the total profit, which one is largest? 175 is the largest. So 175 is the optimal solution. We allocate dependent as follows. Area 1 equal to 1, area 2 equal to 3, area 3 equal to 1, because total is 5 repetitive working in 3 different area, such that you have to find the optimal value, that is 175, and that is mentioned in thousand, or that's why I am writing a 175 thousands. That is the maximum profit. So this is actually the solution of the numerical problem on dynamic programming. It is very easy. And this dynamic problem is also used to find the shortest route between two cities. Another example, let us consider. Determine the value of U1, U2, U3 so as to minimize Z equal to, Z is the objective function, Z equal to U1 dot U2 dot U3. And the constant equation is also given, subject to constraints U1 plus U2 plus U3 equal to 10 and U1, U2, U3 greater than or equal to 0. So what is the solution here? Let us state variable xj, and j stands as 1, 2, 3, such as x1 equal to u1 plus u2 plus u3 equal to 10. That is a constant equation. u1 plus u2 plus u3 equal to 10. We consider that is a stage 3. x1 equal to u1 plus u2 plus u3, that is 10 at stage 3. Then I am writing x2 equal to x3 minus u3. x2 equal to x3 minus u3, that is u1 plus u2 at stage 2. Then x1 equal to x2 minus u2 equal to u1 at stage 1. The maximum value of z for any feasible value of the state variable is given by function of x3. x3 is the state variable. Function of x3 equal to max u3 dot f2 x2. Function of x2. Then below you mention what is f of x2? F of x2 equal to max u2 dot f of x1. And what is f of x1? F of x1 equal to u1 equal to x2 minus u2. x2 minus u2. Now you can write it as function of x2 equal to max, that is the maximum, u2 dot x2 minus u2. u2 dot x2 minus u2. Then if you multiply, what happens? u2 dot x2 minus u2 square. If you expand the bracket, automatically it can be multiplied. u2 is multiplied with x2, it becomes u2 into x2, and u2 into u2. u2 into u2 means u2 square. Then differentiate f of x2 with respect to u2. If you differentiate the f of x2 with respect to u2, we have the equation, that is x2 minus 2u2 equal to 0, or u2 equal to x2 divided by 2. If x2 minus 2u2 equal to 0, then what happens? u2 is, what is u2? u2 is equal to x2 by 2. Hence, by using Bellman's principle of optimality, we get function of x2, backward direction, backward process we can implement it here. F of x2 equal to x2 by 2 into x2 minus x2 by 2 whole square. So what is actually answer? x2 square divided by 4, and f of x3 equal to maximum belongs to u3 dot f of x2, that is maximum from u3 within bracket x3 minus u3 whole square divided by 4. Again differentiate f of x3 with respect to u3, we get x3 minus u3 into x3 minus 3u3 equal to 0. Now neither u3 equal to x3, which is trivial as u1 plus u2 plus u3 equal to x3, or x3 minus 3u3 equal to 0, or u3 equal to x3 divided by 3, that is 10 by 3. Therefore, u2 equal to x2 by 2 equal to x3 minus u3 divided by 2, that is 10 by 3. Similarly, u1 becomes x2 minus u2, that is 20 by 3 minus 10 by 3. We get 10 by 3. Thus, u1 equal to u2 equal to u3 equal to 10 by 3. And hence, makes u1 dot u2 dot u3 equal to, so 10 by 3 into 10 by 3 into 10 by 3. So you get 1000 divided by 27. So this is actually the another problem we can solve by using Bellman's principles of optimality. Again, I am summarized from the beginning. So in today's class, we first know dynamic programming. Dynamic programming means what? It is a mathematical technique to split a larger problem into different subproblems, and the subproblems is known as your states, and the link between the two different stages is called as your state variable. The mathematical technique for optimizing a sequence of interrelated decisions over a period of time is called dynamic programming. And this dynamic programming problem is used to solve the LPP. Then we know what is the difference between dynamic programming and linear programming. As we know that in linear programming, there is a certain algorithm, fixed algorithm to solve the problem. But in dynamic programming, there is no set procedures to solve a decision problem. And linear programming approach provides one time period solution to a problem, whereas dynamic programming approach is useful for decision making over time and solve each subproblem optimally. Then we know the important terminology. One is your state and return function. Then what is actually decision tree and Bellman's principles to find the optimal solution. Then we know the characteristics of dynamic programming. We may implement by using the forward computational process or backward computational process. Then we know the algorithm of dynamic programming. Then the two stages, how to solve the problems and explain with the numerical problems on dynamic programming. And one LPP problem to find the optimal solution. Thank you.